Hello everyone. We are doing chapter 1. The purpose of chapter 1 is to understand the basic concept rather than doing some realistic real problem. Okay, so we have made the problem simple. That is, we make one DOF problem or two DOF problem to understand the basic concept. Let's go to the second week lecture. Okay, so I'd like to review of last lecture. Firstly, the system, if you remember, there are a perfect system and imperfect system. In perfect system, we do the bifurcation analysis. For imperfect system, we do low diffraction analysis. We have two different analysis: equilibrium method and energy method. We assume two different diffractions: small diffraction theory and large diffraction theory. And then this is a perfect system. There is no crookedness, initial some imperfection or initial some deformation before loading apply. Okay, it is a perfect system. This is imperfect system. We have the initial imperfection theta 0 before loading apply. So we can draw the displacement load relationship. Okay, this is a fundamental path. Okay, we call it fundamental path up to the bucking load or bifurcation point. Okay, in order to get the bifurcation point for bucking load, we assume small diffraction theory, and then in the perfect system. Okay, after a bifurcation point, we can get the post-buckling path in perfect system. In post-buckling path, as you see, we consider the large diffraction area. Okay, so large diffraction. Another term is that equilibrium path. If imperfect system, that means we have the original deformation when P equals 0, original imperfection. Okay? And then it is a large diffraction problem. Okay, so we call it equilibrium path. This week I'll show you two examples, and I also explain type of stability and design philosophies. Okay. Okay, let's see example 2. This is a rigid bar problem with translation spring. This is a rigid bar. This is a translational spring. Last week we begin perfect system, small diffraction, and then we move to imperfect system, large diffraction problems like that. But in this problem, we will start with imperfect. That means we have theta 0. And large diffraction problem, this is rigid bar, original deformation theta 0 LP, theta 0 disposition. So it moves up to theta. Then this projection, the length on horizontal surface is L cosine theta, right? And then original the position theta 0, so L cosine theta 0. This length is L. So this P originally stay here, okay? Here and then move forward. Here is L cosine theta 0. This one is L cosine theta 0. This gap, it moves. Then the spring is originally like that. This position, it moves up to here. So the displacement is L sine theta minus L sine theta 0, this angle. Then we can get this length. So L sine theta minus sine theta 0. That is that translation of this spring. Okay, so from this configuration, we can get the internal energy. Internal energy, the equation is 1 over 2 Ks delta square. That is internal energy. So this is delta, L sine theta. This is the stress energy in the spring. So the spring's displacement is this one. Okay, that one. Okay, so L sine theta minus sine theta 0. So delta square. Okay, this is delta square. This is potential energy P. Original position here to move to here. Here move to here. So PL cosine theta 0 minus PL cosine theta. So this is potential energy. Potential energy decrease, so minus. Strain energy increase, plus, right? So total energy is strain energy plus potential energy. Okay, equation. This equation can be written as, and then we can take the derivative against theta. So from here you can get ks s square, this square, and then sine theta minus sine theta 0, and then derivative sine theta and cosine theta minus pl cosine theta 0 is constant value, so disappeared. Cosine theta minus sine theta, so minus minus plus sine theta minus pl sine theta, like that, should be equal to 0 for equilibrium. So equal to 0. From this equation we can get this P, like that. If you move this part, this below, then you can get this one. It is called equilibrium path because it has originally some initial deformation without any loading. So it is imperfect system, and then we call it equilibrium path. From this one we can get many values. If theta 0 equal 0, that means there is no initial imperfection. There is no initial deformation. Then we call it perfect system. From here, we start from imperfect system, right? That means theta 0 exists. But from this equation, we can make perfect system. How to make? Just setting initial imperfection delta 0 equals 0. So this term diminished, okay, disappeared. Then the remaining one is KSL cosine theta. Yeah, this one. This one is KSL cosine theta. This is post-buckling path. Theta, cosine theta remains, so large deflection problem. Post-buckling path and large deflection problem. From here, if we assume small deflection, cosine theta equal 1. Assuming small deflection. So we can get critical load. PCR equal KSL. So we can get the critical load post-buckling path from the equilibrium path. Now we are using some energy approach, so we can get some nature of stability. How to get? We can take second derivative against theta. So this is the first derivative. So we can take the second derivative against theta. From here, we can get ks l square cosine square theta minus sine square theta sine theta 0 sine theta minus pl cosine theta, like this. Now after that, we plug in P equation into here. So P equation is this one here. P equation plug in, and then we rearrange this equation. We can write KSL square minus sine cosine sine, like that. So we can make the theta 0 as a denominator. Then we can dominate the values like this. Here sine square theta cosine square theta equal 1. Why? So sine theta 0 remains this term, and then minus sine third theta, like that. Here as you see, theta pi over 2 minus pi over 2 equals sine theta equal greater than 0. If this equal greater than 0, then this second derivative values is positive. That means it is stable. So this is less than 0. That means these values is negative, right? So unstable. Here, if you draw, this is pi over 2, okay? Plus pi over 2. This is equal minus pi over 2. From this equation, if we assume the initial imperfection, theta 0 equal 0.1. From this equation, 0.1 here, theta 0.1 radian, then you can get theta equal less than 28 degree. Okay, then we get the stable. Okay, that means theta equal 0.1 less than 28 degree, then it is stable. That means the curve go up like that, After 28 degree, it is going down because this one is minus value. If theta 0 equals 0.3, we assume like that, then if theta equal less than 42 degree, then we get the stable. That means theta equal 0.3 and goes up to here. This degree is 42. Okay, this area is stable. If theta is greater than 42, it is unstable like that. That is some equilibrium path. Stable, unstable, stable, unstable, stable, unstable, stable, unstable, like this. That is the nature of equilibrium path. By investigating the sign plus or minus of second derivative. Okay. Another one is, this is equilibrium path. Equilibrium path is P equal KSL cosine theta 1 minus sine theta 0 sine theta. That is equilibrium path. Depending on the initial imperfection, we have infinite number of equilibrium paths, right? So at this moment, we try to get this peak point. How to get? From this post-buckling path, this peak point, slope of this, the curve equals 0. So how to get the slope? dp over d theta. So we take the dp over d theta, then okay, cosine minus sine minus cosine. You take derivative of this one. And we can write like this, and then we can this equation simple as this. So this the slope equal to 0. If you see this point, the slope equal to 0, so equal to 0, then you can get relationship sine theta 0 equal sine cube theta. Okay, like that. So you plug in this value into this equation. Okay, KSL cosine theta 1 minus sine theta 0 equals sine cube theta, like that. Then you can get the 1 minus sine square theta. That means cosine square theta. So ultimately you can get KSL cosine cube theta, like that. This one is some peak value curve of equilibrium path. This peak value, that means this line. Oh, we can also get this kind of curve in addition. Okay, that is example 2. So far you did one DOF problem because you have one rotational spring or one translational spring. I'll show you two DOF system. You have a 2 degree of freedom. Yeah, this is beam, and then you have spring KS. You have identical spring value here, but here the problem, we have to get PCR. So in order to get PCR, you can think, oh, this problem is perfect system or imperfect system. What is the answer? It is perfect system, right? Because we have to get the PCR. Another question is that it is a small diffraction problem or large diffraction problem. Yeah, it is a small diffraction problem. Why? Yeah, in order to get the PCR, we have to assume the small diffraction problem. In small diffraction problem, sine theta equal theta, right? Cosine theta equal 1. That is small diffraction problem. Okay, let's try to get the PCR. From this original member, we can consider this kind of deformed shape. A, B, B, C, C, D, like this. This is deformed shape. So here the rotational angle is called theta 1. This one is theta 2. So we have two different rotational angles. So it is 2 DOF system. So if we assume theta 1, theta 2, this one is L sine theta, right? But it is small diffraction problem. You can write sine theta 1 equal theta 1. Okay? So L theta 1. As the same way, this equal L theta 2, right? How about this distance? L theta 1 minus L theta 2. Then we can get this angle equal theta 1 minus theta 2. L theta 1 minus theta 2 equal this value. So based on the small deflection assumption, angle equal theta 1 minus theta 2. This reaction RA equal 0, RD equal 0. Do you know why? If you take the moment here, this 2 P goes to this, so there is no moment due to P, okay? So you have the moment RA times 3L, and then there is no any other moment. So RA 3L equal to 0. That means RA equal to 0. So sigma Fi equal 0, then RA equal 0, RD equal 0. Okay, so there is no vertical reaction in this system. And then we have to calculate how much this Ks rotate. Let's calculate this point rotate. Here AB. If we consider the straight line, then BC. Originally, they are straight, okay? So you have to consider from this straight line and then how much this member move. You consider like that. So if this BC is straight, there is no rotation between this AB member and BC member. But as you see, it is not straight. It moves. That amount is some rotational angle. So as you see here, it is somewhat complicated. If you make this horizontal line, this is theta 1, then this is theta 1. Theta 1, theta 1. This angle equal theta 1 minus theta 2. So this rotational angle equal theta 1 plus theta 1 minus theta 2. That means this angle equal 2 theta 1 minus theta 2. That is the rotation of this member, okay, from the original the position. So the moment due to this rotation is Ks 2 theta 1 minus theta 2. And then let's look at this part. If you consider this straight line, and then horizontal one. As you see, this one is theta 1 minus theta 2. This horizontal line and this angle equals theta 1 minus theta 2. This horizontal and then this straight line equal theta 1 minus theta 2. As you see, the theta 2 here, this straight line equal theta 2 because this horizontal straight, this theta 2. The angle change from this straight line, the theta 2 minus this angle. Then is remain this angle. Okay, so theta 2 minus this theta minus theta 2. That means 2 theta 2 minus theta 1. That is the rotation of this member from this straight original position. So this is the moment. That is the angle relationship. And the left hand side you have the free body diagram. You can get the equilibrium. Okay, this is the moment Ks 2 theta 1 theta 2, and then opposite direction, so minus P and this distance L theta 1, right, equal 0. Right hand side you have the rotational moment equal Ks 2 theta 2 minus theta 1, okay? And then P times L theta 2. This is L theta 2. That is equilibrium equation. If you rearrange this equation regarding the theta 1 and theta 2, you can rewrite like this: theta 1, theta 2. Then if you write this equation in matrix form like that, for non-trivial solution, if theta 1 equals 0, theta 2 equals 0, then this equation satisfies 0, but it is trivial solution. That solution is not what we want. In order to get the PCR, this determinant of this matrix should be 0 from math. So if you take the determinant like that, equals 0. Now, from this equation, you can calculate like this. Yeah, rearrange like that. Then you can get P equal 3 Ks over L, Ks over L. You have two solutions because this problem is two degree of freedom system. That means you can get two PCL, two eigenvalues. From the critical loading is the smallest one is critical loading. PCL equal Ks over L. From these two eigenvalues, you can get eigenvector. If you get the eigenvector, you can see the buckling shape. So from this P equal 3Ks over L, if you plug in these values here or here, one over these two equations, then you can get the relationship of theta 1, theta 2 equal 1 minus 1. Another eigenvalue, P equal Ks over L, you can get plug in those equation above, then you can get theta 1, theta 2 equal 1, 1. Okay? So, if P equals 3Ks over L, theta 1 equal 1, this direction, minus 1 equal the minus, opposite direction, like that. That is the mode shape. Okay? Second mode shape. The first mode shape is this one. Theta 1, theta 2 is identical, so same direction, corresponding to our assumption. That is first mode. Okay, it is 2 DOF problem. We can solve this problem using an energy approach. So internal energy equal Ks to theta 1, theta 2, right hand side term, left hand side term, and then potential energy equal, as you see here, this length decrease, just some length shortening. We calculate that shortening like that. PL 1 minus cosine theta 1 minus cosine theta right hand side and the middle part. This is the total energy like that. For equilibrium, you take the derivative. So 2 DOF problem. So we have two different derivative regarding theta 1 and theta 2 of this equation. You can get this equation and this equation. A perfect system, so it is a small deflection problem. Sin theta 1 equals theta 1, sin theta 2, theta 2. And then if you rewrite the matrix form like that, then in order to get the solution, you can take the determinant. Then from this equation, you can P equal Ks over L, 3Ks over L. So you can get the same PCR. If you plug in these values, then you can also get the same mode shape. Plug in this equation or that equation. So we did a 2 DOF problem. So 2 DOF problem, you can get a 2 by 2 matrix. If you solve 3 DOF problem, you will get 3 by 3 determinant. Then you will get 3 critical values. Okay, 3 P's. Okay, let's stop here.